Welcome to the Open Innovation in Chip Design workshop by Object Automation, hosted.
Peter Hofstee is a physicist and computer scientist who currently is a distinguished research staff member at IBM Austin, USA, and a part-time professor in big data systems at Delft University of Technology, Netherlands. Hofstee is best known for his contributions to heterogeneous computing as a chief architect of the synergistic processor elements in the cell broadband engineer processor used in the Sony PlayStation 3, and the first supercomputer to reach sustained petaflop operation. After running to IBM research in 2011, he focused on optimizing the system roadmap for big data, analytics, and cloud, including the use of accelerated computing. His early research work on coherently attached reconfigurable acceleration on Power 7 paved the way for the new coherent accelerator processor interface on Power 8. Hofstee is an IBM master inventor with more than 100 issued patents. We welcome you, sir.
Thank you so much for the kind introduction. So the audio is good now, and the video also seems to be good. So I'll start presenting. And again, if somebody wants to record, then that is fine with me. So I'll start sharing my screen here. And then go to presentation. So I hope this is visible. So what I will do is I will tell you a little bit about my background, which because most of my work at IBM has been affiliated with the power architecture and systems. I think that might be a nice way to start. Then I'll give a background on the open power instruction set architecture, which defines what PowerPC and open power is. And then I'll talk about some of the open power cores that are available within the ecosystem. So this chart is a kind of a summary of some of my professional history at IBM. So when I joined IBM in '96, first thing we did is we developed the first gigahertz processor based on power architecture, and this was at a time when I think the fastest processors were 300 megahertz. So that was a very nice way for me to start at IBM. Actually, prior to that, I had done an internship and also worked with one of the very early RISC architecture-based PC system at IBM. And then, after that, I worked on one of the game processors, the PlayStation 3 processor that also was mentioned here in the introduction. The cell architecture, the heterogeneous architecture that combines power with acceleration capabilities. A version of that was used in the Roadrunner supercomputer, which was the first one to reach a petaflop of sustained operation. And then I worked still on heterogeneous computing, but more at a system level, working primarily with FPGAs and the coherent attached interface that allows memory sharing at a system level. Where previously within the PlayStation 3 we had done it within a CPU. So basically extended these concepts to a system level. CAPI has been contributed to the CXL consortium. So the future of that technology is the CXL standard, which is the follow-on to PCI Express. Also, as mentioned in the introduction, I've worked on big data systems. In particular, we had a hyperscaler at Tencent in China that deployed some of the power systems at a large scale for their big data problems. I was also a little bit less directly, but I was also involved in some of the Power 9 based supercomputers, Summit and Sierra, that again were the leading supercomputers. And then currently I'm working on the power enterprise systems that IBM does, and I have another slide here. So these systems are used across the world, primarily in large database and banking type applications, but not exclusively to banking. All other large databases often run on these systems as well, and they're indeed very large system. One system occupies the bulk of a rack, supports up to 64 terabyte of memory, and this is not drives. This is 64 terabytes of DRAM. Up to 1920 threads. Right? So if you were to have a little Linux symbol, a little penguin for every Linux thread that starts, you'd have 1920 penguins if you fire this machine up. In immense amount of bandwidth, and these systems go up to 16 sockets, and each socket has a terabyte per second of memory bandwidth and a terabyte per second of bandwidth connecting it to the other sockets. And it runs a variety of operating systems. The Unix operating system that IBM has had for quite a while is called AIX, but we also run Red Hat operating system. SUSE, Linux, Red Hat and SUSE are both Linux operating systems. And then IBM I systems, that are, DB2 is IBM DB2 is a key application for IBM I. Those systems are using the same hardware foundation. And as I mentioned, it's used primarily for large databases. What I hope might be interesting to this audience is that in the future, these types of systems will be designed top to bottom in India. And by that, I mean we will design the processors in India. We will design the systems. We will design the firmware. We will work on the operating systems. All of this will be done primarily in a couple of labs in Bangalore. But a number of other IBM locations across India as well. So I think this is an exciting development. I know that India has contributed to many similar processor and system design efforts over the years, but this might be the very first time that an effort like this of this scale and this advanced is actually being driven completely out of India. So now I'm going to talk about open power, and there is the Open Power Foundation, and let me just briefly show you. If you go to openpowerfoundation.org, and this is where the entry point you will see. There are many things here. First thing I want to mention is that for academic institutions membership into this organization is free. And amongst the things that you will see here, if I look under technical specifications and then go to instruction set architecture, this is where you will find the most recent version of the Power instruction set architecture that, as I mentioned, defines what it is to be a power processor. Let me go back to the PowerPoint. Go back to slide. All right. So for a bit of history, so even though the term RISC, reduced instruction set computer, was coined by the team at Berkeley that developed MIPS, the work on that type of an architecture at IBM actually preceded the work at Berkeley. It started off with IBM being asked to provide a next generation telephone switch, which was a project that started in 1974. The project ultimately was for I think business reasons, it didn't complete, but it led to the ideas about having a processor that would be more efficient than the complex instruction set computers and processors of the day. So it continued as a research project called 801, which is one of the buildings in Frisco, New York, where this project was continued. And the lead of it was John Koch. You see a picture of him on the right there, and a link to a website. That 801 processor ultimately, went through some iterations, and some early products, in particular the IBM PC-RT that I mentioned, where when I joined IBM for an internship, I think in 1991, I worked on that, as well as an early RS-6000 that was more of a workstation type computer. So these are the early work there, and then from 1990, there has been a long series of products used in many different domains. So on the IBM side, we have the Power processors, Power 1. We're now up to Power 10 in the market, and this series will continue. Apple, Motorola, and IBM had a joint effort called Somerset, where many generations of processors that were used in Apple computers, as well as in network and automotive and other applications by Motorola, eventually leading to an architecture that is compatible with Power architecture from a user program point of view, but that had a somewhat different address translation organization called PowerPC Embedded. So for a while there, we were having two different architectures, one that was used primarily for servers and one that was used primarily for embedded type applications. And then around 2017, we started working on the Open Power ISA. So we've converged into a single architecture now, and the latest version of that is this 3.1c that you can download. And the Power architecture is now managed within the Linux Foundation. And it's an open architecture, and if you build compliant implementations of the Power architecture, and I'll talk more about what it means to do a compliant implementation, then it's not only open, it's actually license-free. So that makes it very attractive, we think, for on the one hand, academia. This is an architecture that is very open, and also there are possibilities for introducing customization and doing innovation, and then those things can flow back into the Power Open Power Foundation and into the Power architecture. Over the year, what you see here is that the number of instructions really has grown substantially. And so it's the characteristics of having an architecture where you move things between memory and a register file, and then have operations on a register file. Actually, now have multiple register files within the Power architecture for scalar, floating point, VMX type operations, SIMD operations. That characteristic remains, but there are many different instructions that have been added over the years, and I'll mention some of them in upcoming slides. So this just says that we are now managing the architecture under the Linux Foundation. I won't go into this in a lot of detail, but we have the definition of the architecture has been split into book 1, book 2, and book 3. So book 1 is where user code would normally run, and then we have the other layers of the architecture that are used for operating system like functions, and then ultimately actually the operating and hypervisor functions. So there's a split there. So now let me talk a bit about the how we've structured the architecture, and I'll do that based on the slide here. So at the bottom here, you see what it would mean to be fully compliant with the architecture and support all the 1419 instructions. So that is a fairly substantial task to develop a processor that supports all of this. But it's actually very easy to get started. So we've defined a scalar fixed point subset, and this is the smallest set of instructions, just 129 of them. And you can have very straightforward and small implementations that implement this. Then there is the scalar fixed point subset that adds, scalar fixed point and floating point that adds the floating point operations to it. So that's the next compliant set. So you can choose to only support this, or you can choose to support both of those. And then adding another set of instructions, which actually includes the SIMD instructions. You get to the subset that is assumed when you build the Linux operating system. Now, as it actually turns out, the Linux operating system largely depends on the scalar fixed point subset, and then just a few instructions from floating point and the SIMD instructions, in particular, sort of block move instructions. And then there's another set of instructions where we've added instructions to support the AIX operating system. So we go into a little bit more detail here. This is the same hierarchy. You see that when you go to the Linux subset from scalar fixed point and scalar floating point, which is kind of obvious what those are, you see support for logical partitions. This is a hypervisor thing. We run Linux in little endian mode. So Power architecture definition is by endian, can be either little endian or big endian. But Linux requires little endian mode. So, to support this, you have to implement little endian or both. Linux now depends on support for radix address translation, so that has to be supported. And as I mentioned, it uses some of the SIMD instructions, and it it depends on 64-bit mode. So you can run Power architecture in either 32 or 64-bit mode, but our Linux support assumes 64-bit support. And then above this, I won't spend much time on this, but if you go to the AIX subset, there are a number of instructions and operating modes that have been used in the past. When you build these very big systems, an example is here, the translation look-aside buffer invalidate entry. When you work on very large systems, that kind of thing has to be very efficient. So there's specific instructions that help, for example, when you need to invalidate an address translation, help make that kind of thing more efficient, as well as some instructions like decimal float is used by the banking industry, etc. Our AIX, our Unix is big endian, right? So if you support the AIX subset, then you have to have support for actually both little endian and big endian. And then there are, besides these different layers that I mentioned, there's also other aspects of the architecture. I'll go into a little bit more detail about on this matrix math assist function, where you have a choice to either implement them or not, but it's somewhat orthogonal to this hierarchy here. And then, so besides the compliance subsets, we've also carved out pieces of the registers and the opcode space. And so certain special purpose registers, exception registers, condition registers, interrupt vectors, and a particular opcode has been reserved for people to do their own custom implementations. So, you might encounter this later in the workshop, but I've put together an example of adding some custom instructions that could be useful for building something like a spiking neural net implementation on Power. And if you do that without breaking compliance with the architecture, you have to use this primary opcode 22. So this is how we allow and encourage innovation within the architecture. Now, of course, when you add your own special instructions, the tools are not, the compilers, etc., are not going to know about that, right? So if you want to leverage the support in Linux and in the software ecosystem, then you have to stick with the instructions that are already defined. But if you have a good reason to add some custom instructions because you want certain functions to be very efficient on your implementation of the Power architecture, then you can do that. But of course, in that case, you have to make sure that you add the software support for it yourself as well. Now, again, Power architecture is set up as an open community. So if you're developing something that you think could be broadly useful in the architecture and maybe in the future should be supported by the standard compilers, etc., and then what you can do is bring a proposal to the architecture committee under the Linux Foundation and have this become a part of the architecture in the future. And it's works the same way that the open source software projects work, right? So you make a proposal to make a modification to the architecture, and then the community has to discuss that and adopt it. Okay. In the latest version of the architecture, there's a number of things that have been added. I'll go into a little bit more detail about two of them: the matrix math assist and prefix instructions. So we've had the SIMD type capability in the architecture already for some time, but primarily because of the interest in AI, we've added matrix functionality in the architecture, right? So this allows for efficient execution of the matrix type operations that you'll find in such things like deep neural net, DNNs, deep neural networks. And what we've done is we didn't include yet another register file. We have accumulators that are associated with groups of 4 vector registers. So the accumulators are 512 bits wide each, and then we can move the contents of the accumulator into a set of 4 vector registers, and then from there move it back and forth to memory. So we have 8 of those accumulators, and the way the matrix operations are organized is as outer products. So you know, to create for example, a 4x4 matrix of 32-bit elements. So this is 16 32-bit elements. So that adds up to 512 bits in an accumulator. You can do that by doing 4 you know, rank 1 updates of outer products of you know, 228-bit registers, right? So 4 of those, you know, can be done at the same time, you know, being accumulated into a matrix like this, right? Again, keep in mind these accumulator registers are 512 bits. And then I don't have time here to go through the details, but you can do that for, you know, smaller quantities as well. And then you know, you can, every time you go to a smaller quantity, you can double the number of operations that you can do concurrently. And in the slides, I have there's a link to a presentation that goes into more detail. So if we look at, for example, the Power 10 implementation of this matrix math assist function, you see that on a single core of the Power 10 architecture, you can do up to 1,000 operations per cycle, right? So if you know, run a processor like this at say 4 gigahertz, right, then you would do 4 tera operations per core, right? And then, you know, of course, we have many cores in our systems, and each core could do up to 1,024 4-bit operations every cycle. Now this here, of course, is microarchitecture, not architecture. So there could be other implementations of this that have, you know, do more or fewer operations per cycle per core. The other thing I'd mention is prefix instructions. So the Power architecture, for the longest time, every instruction was 32 bits, but primarily because you know, memory in our computers is getting so large that you know, the 4 terabytes that you can reach within 4 gigabytes that you can reach within a 32-bit value is really constrained. And that means that if you have a large program and you need to jump around, then you would actually need you know, to load something into in the Power architecture. We do this through the link register and then branch, and so there was a fair amount of inefficiency. So we now have a prefix instruction where for certain instructions, the instruction actually is 64-bit, and in particular that allows us to have you know, larger branch offsets, as well as you know, larger constant values for certain operations. It also has the effect that we now have, and again, I won't go into the details, but we have a lot of space now in the in our opcode map for you know, for the future to you know, add yet more capabilities to the architecture. So in summary here, for the ISA part, right, it's an open and license-free architecture for, you know, for compliant implementations, right? So we do want to make sure that if something is called an open Power or PowerPC architecture, that it will actually run PowerPC programs. So that's why we do insist on compliance. But I hope I indicated to you that there is a lot of flexibility here. You can have very small compliant implementations. You can have compliant implementations with a custom aspect and do innovation. And you can have very complex ones. And it's maintained by the Open Power Foundation. So now let's take a look at some of the cores that are available in the Open Power ecosystem, and I'll touch on 3 of them. So microwatt is a core that I think you will look at quite a bit more within this workshop. And then there are also 2 other cores that we've put out, for the community to use. So these are freely available cores. So microwatt is a very, very small core. It does the scalar subset, and actually now has done a number of the includes the prefix instructions. And you can actually boot Linux on this small core. So I think that's very exciting. You have you can build this on an FPGA, and then actually I've been using an RT small FPGA development board. And it has an Ethernet connection and so on. And after I boot the operating system, I can talk to the system over the Ethernet. It's a fairly simple 6-stage pipeline. Actually, I think we may have broken this into 2 stages now. So it's written in VHDL. It's fairly easy to understand. Let's just take a brief look. I think you will look more at this during the workshop. But here is a set of instructions that I've put. So if you go to this, GitHub site Hofstee.hp, and go here. So microwatt was developed by Anton Blanchard and a number of colleagues, and the source for it is here. What I've done is, because it still can be a little bit tricky to build a processor, because it might assume that certain packages are installed in your Linux image, etc. I tried to give a set of instructions that is completely from scratch, starting from a basic install of Ubuntu and going through all the details of how to build it. And I think you might be looking at that or a similar set of instructions in this workshop. And then there's also an example in another subdirectory about if I defined 4 new instructions that are not yet in the architecture, and I go through the details of exactly which you need to modify and how to add custom instructions. Hopefully, you could use this as a template if you would want to add your own custom instructions and create your own version of a power processor. Okay, let me go back to this. Besides this, microwatt, which is meant to be a very, very easy entry point, there are a couple more complex processors that we've also put out in open source, called A2I and A2O. A2I was used for a Blue Gene supercomputer. That processor has 4 threads executing in a core. It actually is doing like a multiplexing these four cores, 4 threads within a core. And then there's an out of order processor, A2O, which actually has 2 threads per core, but is more complex. It's out of order execution. I think one of these, at least one of these, is written in Verilog rather than VHDL. I think the other one may be written in VHDL. That they're somewhat more complex. They were used in fairly complex SoCs for this Blue Gene supercomputer and other applications. The original version of these is using that embedded architecture that I've referred to earlier. So there's some minor changes that need to be made to make it compliant with how address translation works in the current version of the ISA. But these are still, one core is still fairly small. In 45 nanometers, it'd be 3 square millimeters. If you do it in a somewhat more modern technology like 7 nanometer, it'd be like 0.2 square millimeters. The cores can run quite fast. It's multiple, our implementations of it ran at multiple gigahertz, and they're still small enough so that you can also implement it in an FPGA. There was also a network type processor that was actually went through a full development cycle, but for, again, business reasons, didn't become a product, that was using 4 of those A2I cores in conjunction with some other IP in an SoC. This shows a little bit more detail of how that microarchitecture works. What it's capable of, and again, if you take one of these A2I cores, you can realize it on an FPGA. In that case, you need a somewhat larger FPGA than you could use for the microwatt processor. But we have examples of building this core as well as the A2O core on an FPGA. I've made the slides available. There's a number of talks as well as pointers to some additional material. So I think I will leave a little bit of time for questions here. So in summary here, I hope I've given you an indication of a long and storied history going back about 50 years now with RISC and then the power architecture, and it's been used across a very, very wide application space through the different generations. IBM is currently focused on scalable server systems, and as I mentioned, the next generation of these systems as well as the processors for those systems are being developed here in India. So there's going to be a lot of local expertise on the architecture. And while IBM will be focusing on these server systems, we are very interested in encouraging other people to use the architecture for other purposes. And I've had numerous conversations with universities and even companies, about things that they might like to do with the architecture in the future. And while building a world-leading microprocessor, say for servers, is a very substantial undertaking that costs hundreds of millions of dollars and design teams of many hundreds of people. The smallest compliance subset are actually easy to deal with for even just a person by themselves in a part of their time. And the microwatt processor is a great way to start. So with that, I will leave some time here for questions. I'd be happy to try and answer.
Any question, please? can ask directly.
And I'm not sure I can hear the room directly. So if there is a question, maybe somebody could repeat. I know it was a bit of a fire hose. There's a lot of, a lot of different stuff. As you go through the workshop, I'm sure you'll touch again on many of these things, and you'll have opportunity to ask questions then as well. And, yeah. So again, for me personally, my career at IBM has been very much, aligned with the power architecture. I've had an opportunity to personally experience, some of the breadth of things that can be done with power, from game systems to supercomputers.
Okay, bye.
Any questions?
If you don't have any questions later on, also you can send the questions to us. Peter definitely will answer them.
I'd be happy to answer questions by email. No problem. And again, I know that this was a very quick run through. Right? So through the workshop, you'll revisit many of these things, at a somewhat more reasonable pace. So, but yes, if questions come up later, I'd be happy to try and address them through email. So again, thank you for participating in this workshop. I'm very excited that so many institutions in India are taking a look at this architecture. Best of luck with your future projects.
Thank you, Peter.
All right, so with that, then I think I will sign off.
Thanks have provided us with a deeper understanding of this exciting process. We really appreciate your time and experience.
Thank you.
All right, thank you so much. Bye-bye. Bye-bye.
Thank you. Thank you all.